Okay, so we're now recording. So it's a pleasure to introduce Michael Puschnigg from the University of Marseille, who I'm known for, I think, 35 years. So his talk today is on periodic cyclic homology of cross products. Please, Michael, go ahead.
Thank you very much, Guillermo. Yeah, it's a great pleasure for me to talk in Buenos Aires. It would, of course, be an even greater pleasure to be there in person, but one cannot have everything these days. So, yeah, so I'm fine with being able to talk to you. So, as you pointed out, my talk is about the cyclic homology of cross products. Homology of cross products. Now, what is this? There's a problem with my cross products. So maybe it will go away if I write essentially on the center here. I mean, this is one, to begin with, this is one of the oldest calculations and maybe the first significant calculation of the cyclic homology of genuinely non-commutative algebras. And I will present a new proof of this, a new approach to this. The structure of the talk will be the following. First of all, I will recall the work of Burgili and Nistor, who did this calculation in the late 80s. Then I will explain why one might be interested to have another approach. Yeah. Then I will present now my approach to this calculation, and then I will outline a couple of applications. So let me just start with a setup. So we will fix now here a field of characteristic 0. Yeah. And an abstract group, G is a group. And we will suppose here, just for technical reason, that the cohomological dimension of the group over K should be finite. I mean, this restriction is of G, excuse me. This restriction is in the end completely unnecessary, but I want to get formulas which just use well-known invariants. And that's why, to simplify notations, I suppose that the cohomological dimension should be finite. Okay. So
sorry, does that mean every module of the group algebra over K has a solution of finite size?
It means that you get a projective resolution of the constant G module K by projective KG modules of finite length. Yeah, so there is a finite resolution by projective KG modules over the constant G module K. And A is supposed to be a G algebra, okay, or KG algebra. And then you may form the cross product. And to recall what the cross product is, the cross product of A by the action of G. So as a vector space, this is just A tensorized over K with the group algebra KG. And the multiplication is such that the product of a basis element, let's say AUG, by another basis element BUH is just. Now the idea is that whenever you pass a UG across an element in the algebra, whenever you pass a basis element of the group ring across an element of the algebra, then you act on the algebra element by this group element. So you get A times G of B times UG GH. In other words, the G algebra on A becomes an inner action on the cross product, and the cross product is universal with respect to this property.
Sorry, one question. What, when you say A is a KG algebra, what exactly do you mean? I mean,
it's so to say a K algebra with a G action. It's a K algebra.
But it's not okay. So it's not an algebra over the group algebra.
No. Okay. I should be. It's a G algebra over K. Excuse me, G algebra. Thank you very much. Over K. Okay. So that's the setup. And now I want to excuse me, I have to put this somewhere. Now I want to review the work of Burgeli and Nistor. So this will be paragraph 1. The work of Dan Burgelia. Yeah, from 1985, so it's really very classic, and of Victor Nistor, which dates from 1990. So Burgelia calculated the cyclic homology of group rings, and Victor Nistor calculated the homology of cross products. Fine. So now the key step, the key observation in their approach is the following. When you look at the functor from bimodules over the cross products to the category of vector spaces, the functor which attaches to an bimodule over the cross product, just the commutator quotient M modulo the commutator of M with a cross product, then this functor can be actually be written as a composition of two functors. Namely, you may first just take the commutator quotient with respect to the algebra A. So you take M and you divide by the commutators with respect to A. This gives you a functor from AG bimodules actually to the category of G modules. Because here, whenever you have a bimodule over the cross product, you have a G action on the left, you have a G action on the right, so you have an adjoint action. And this adjoint action passes to this quotient. And then you may do the following. You may pass to the G co-invariance under this action. So you take the largest quotient with trivial G action. This gives a functor here, and this will send this G module actually to the commutator quotient here. So this is a simple calculation, and you observe immediately that all three functors are right exact, and that the functor here, which attaches to an A cross product G bimodule, just the commutator quotient with respect to A, sends free bimodules to free G modules. So homological algebra tells you that when you pass to derived functors, that the derived functor of the passage to the commutator quotient here, and this means the functor H star of Hochschild homology of the pair M and the A cross product with G viewed as bimodule over itself. So we are here over the cross product. That this is isomorphic. So you just have to compose the derived functors of the individual functors here. Now the derived functor of passage to G co-invariance is just the group homology, or here, because we apply it to complex, it's the hyperhomology of the group G, and it has to be applied just to a complex representing the derived functor of the passage to the commutator quotient with respect to A. And this functor is, for example, represented by the Hochschild complex with respect to the algebra A of the A bimodule M and A viewed as A bimodule. Okay, so this is a very nice formula expressing the Hochschild homology of a bimodule over the cross product as hyperhomology of the Hochschild complex just of M viewed as an A bimodule. What interests us is, for us of interest is the case that M is just the cross product viewed as bimodule over itself. And in this case, we deduce just that the Hochschild homology, as it is usual done, noted of the cross product. This means the Hochschild homology of the cross product A cross product G viewed as bimodule over A cross product G becomes just isomorphic to the hyperhomology of the group G with coefficients in the Hochschild complex with respect to the algebra A of the cross product here and A. Okay, now there are two observations, or one immediate observation is the following, that, or no, before I make the observation, I should explain a bit here, because here we have a chain complex, and I want to make explicit the G action with respect to the homology. So the G action on A is clear, but the G action on the group ring here is by conjugation. And now you know that when you act on a group ring by conjugation, it will not be an irreducible module, but it decomposes over as a direct sum over the conjugacy classes. So I can rewrite this as a direct sum over the conjugacy classes of the group G of the hyperhomology of G, and here you take the Hochschild homology just of A, and now you just take in the cross product those terms where you stay inside a given conjugacy class V. So V represents a conjugacy class, and A is here. Okay, so here this is just the linear subspace or the G submodule over the cross product given by linear combinations of elements in the conjugacy class with coefficients in A. Fine. Now, in particular, when you take the simplest conjugacy class, the conjugacy class of the unit element, this shows you that the so-called homogeneous part of the Hochschild homology of a cross product, the homogeneous part contribution of the unit element, is just the hyperhomology of G with coefficients in the Hochschild complex of A. And from this, now you know that there is a standard procedure to calculate cyclic homology from Hochschild homology using the so-called SPI exact sequence. And with this, you derive that the cyclic homology, at least the homogeneous part of the cyclic homology, becomes then the hyperhomology of G with coefficients in the cyclic complex of A. And finally, for the periodic cyclic homology HP of a cross product, its homogeneous part is given by the hyperhomology of G with coefficients in the periodic cyclic complex of A. Okay, so this is what Burgeli and Nistor did, and they do much more because they obtain a qualitative description of the contribution of all other conjugacy classes. Okay, fine. Now, let me say something why one might to look for another proof of this result. Yeah, because I mean, this is quite classical. This gives in principle, a complete answer, or more or less a complete answer. But why am I not happy with it? I mean, there is one thing here, the calculation, and here it's just because it's only, I hope that you know this, the classical calculation of periodic cyclic homology goes in 3 steps. The first step is you calculate Hochschild homology. Then, using the SBI exact sequence, if you're lucky, you are able to calculate the cyclic homology. They are both Z-graded. And then there is a limiting process, a limit process, which leads to the Z2 graded periodic cyclic homology, because the periodic cyclic homology is identified with a derived inverse limit of cyclic homology with respect to a natural operation called Const S operation. Fine. So this is the calculation procedure, the algorithm. So this is the first thing. Usual calculation procedure to obtain periodic cyclic homology. But when you look at it from a functorial point of view, then you see very quickly that these 2 functors have, in some sense, bad properties. They do not satisfy, for example, homotopy invariance. They do not satisfy excisions. Their many nice properties are not bad properties, or not so well behaved, or not well behaved.
I mean, as bad as algebra K theory.
Sorry?
I mean,
excuse me?
Yeah, they are as bad as algebra K theory.
Yeah. Whereas here you have nice properties. Nice functorial properties. Functorial properties. Oh man. Properties, for example, you have homotopy, invariance, excision, and what all you would like. And of course, in a situation where you want to calculate something well behaved by using not well behaved tools, one day, I mean, you will have to pay a price, and I will come in now to this price. A second observation is the following. A second point is the following. These theories here are graded by the non-negative integers, so they may be interpreted actually as derived functors in a classical sense, whereas periodic cyclic homology is only Z2 graded, so it is not possible to interpret it as a derived functor in the usual sense. But I think, or I hope, that all you know the following ultimate version of Bott periodicity due to Cuntz and Hickson. And this says that every functor, every homological functor, it means every functor satisfying homotopy invariance, split exactness, and stability on the category of C-star algebras is Z2 graded. So every, let's formulate it loosely, every homological functor on C-star algebras is Z2 graded. And actually, when you calculate cyclic homology, there is an experience you make that already for Banach algebras, this principle is to be felt. I tried for many years again and again, and I always got a bloody nose. I tried for many, many years to calculate the local cyclic homology of group Banach algebras L1 gamma for some nice discrete groups. And the problem is, it is easy to calculate HH. It is easy to calculate HC. And it's impossible to make this last step, to pass from a Z-graded world to a Z2 graded world. So this is a strong motivation to say, all right, I would like to calculate this for group rings and cross products in a purely Z2 graded setting, just to avoid this problem here. Yeah? And this is what I'm going to present now. And in order to understand what we are doing, I want to make a comment on what is called the derived functor analogy. And this is Quillen who did this. So in a new paragraph. So I do not know what happens that this machine does not work properly, because usually it does. For analogy. And due to Quillen, and this goes as follows. When you look at usual derived functor, let's say you do the following. You start with an abelian category. And you have some, let's say, right exact functor from C to another abelian category. Excuse me, F from C to another abelian category. Then you make the experience that F is not well behaved on complexes. So when you start with an arbitrary complex, the functor will not be well behaved. So what do you do instead? You pass just to a subclass of complexes. You take here, for example, a quasi-isomorphic complex of projective objects. For these, the functor will be well behaved. So you just pass to your functor on this well-behaved complex P. And you hope that all this is independent of the nice projective model of C you use, and you may call it a functor which depends ultimately on C and will be close to F. And this is the idea behind a classical derived functor. Now, what Quillen proposes is the following. He proposes we start with a category of algebras, and we have some interesting functor we want to study and also to write down, which is here much more difficult, to some abelian category. And the idea is the following. So if the functor will not be well behaved for all algebras, but what we do is we replace the algebra under study by a nice model. And this nice model will be some nilpotent extension of the given algebra, such that our functors behaves well on the extension. So we may take f of r. And if we are lucky, this turns out just to be something which only depends on A. And then one would call this the derived functor of f evaluated on A. Okay, so this is a pure analogy. And now we start our approach to the periodic cyclic homology of cross products. So the first thing will be, we will exhibit a nice class of models for a given G algebra. And then we will do the calculation using this nice class. So we use some auxiliary algebras. And by myself, I give a name to them. Namely, I call them stupid algebras. I mean, they are stupid, but pretty useful. I mean, that's something one learns in life, that stupid things may still be useful. Yeah, and so here is one example for this. And this is a quite general construction. So we start just with the set. And the algebra we consider will just, as a linear space, the vectors be the vector space with basis x. So our algebra will be denoted by k, these brackets x, and as a vector space, it is just the span over k by the set x. So it means for every element of x, we have a basis vector, and we will call this basis vector of an element little x. Just we call it like this. And if we have just elements of our set big X, we have basis vectors x and y, and the multiplication will be completely determined if I tell you what the product of two basis vectors is. And the product will be the simplest thing you could think of. The product of x and y is y. And this for all x and y. So it's really not a very sophisticated multiplication. But the first exercise shows you that it is associative. Okay, it is an associative algebra, so easy to verify. And what you observe immediately is that this algebra, such algebras have many, many morphisms. Namely, it's pretty clear whenever you have a f from x to y is a map of sets, then it follows that the induced linear map from kx to ky is a algebra homomorphism. Okay, so it's pretty clear that because when you have a Cartesian square, the product onto the second factor is natural. Now we will use this twice. The first thing is that when we take for y a point, we get automatically a map from kx, just called the augmentation, to the algebra attached to the set with one element, and this is just the base field k. This is obviously surjective, and it is just, like the trivial representation of the group ring. So here you have a linear combination of points, and you just sum up the coefficients. That's the homomorphism, and the kernel is an ideal called I epsilon, the augmentation ideal. And the multiplication now is completely determined by the following condition, that I epsilon squared is equal I epsilon times the algebra. And this is identical to 0. So the square of the augmentation ideal is 0. Not only this, the product of any element in the augmentation ideal with an arbitrary element in the algebra is 0. On the other hand, this algebra is H-unital in a very strong sense, namely every singleton, every base vector is a left unit. So it has plenty of left units, and the many, many products are just 0. So this is the first observation. We have a nilpotent extension. And the second observation is that from this factoriality, it is clear that if G acts on X, if a group G acts on X, then it follows that Kx is a G algebra. Is a G algebra. And moreover, if the action of G on X is free, then this will be a free G module. Okay. Then here, if the action is free, if the action is free, then then it follows that this Kx is a free G module. And so this is, oh man, usually it works. I don't know what happens today with this machine. Okay, module. Fine. Now, before coming to the results, I have still to introduce some notation. Any questions to this? I mean, it's really pretty elementary and simple. Yeah?
Yeah, it looks like a brilliant idea, you stupid algebra.
It looks like?
It looks like a brilliant idea to consider such a stupid algebra.
Thank you very much. I mean, so to say, stupidity meets brilliance. Yeah, that's yes. I mean, we can say, okay, we can be proud to arrive at such a point. Okay, now some notation. So this is something which is pretty clear that you can do it. As with the stupid algebra, the question is only why you should do it. Namely, usually when one looks at cyclic complexes, one works with algebra relative to a field with a basis. But of course, you can also regard algebra with respect to another basis. You may take even a non-commutative algebra as a basis. Yeah. So we look R, for R is a unit of K algebra. It will be in the segment of the group ring. And then you look for an A be an R algebra. So with this means the following. An R algebra means A is a bimodule over R, and the multiplication in A is a homomorphism of R bimodules. Yeah? And of course, also the multiplication factors through A tensor A over R. Okay, but so I'm really very sorry. I don't know why the machine does not work at all today. A is an R algebra. At that point, you can introduce differential forms of A relative to the base R. And so this will be just for, will be the direct sum of, on the one hand, the n plus first tensor power over A, corresponding to differential forms of from A0 dA1 to dAn, but you take the tensor power over R. And then you have the exact forms of the form dA1 to dAn, and they give you a copy of A tensor n. This tensor product is usually taken over K, but here we take it over R. It's pretty clear that you can do it. Now, what you cannot do yet here is you cannot make cyclic permutations we would like to do. And in order to have cyclic permutations, we just divide out by commutators with respect to R. So we take omega n A dot R modulo the commutator of omega n A dot R with respect to R. This is possible because our algebra A is an R bimodule. And on this gadget, you have a cyclic permutation. You can, of course, write down the operators little b, capital B, that you know from cyclic homology. And you have the usual relations that little b squared is, capital B squared is little b, capital B plus capital B, little b is 0. And so this allows you to write down a Hochschild, a relative version of the Hochschild complex dot R, which is just, you take these differential forms relative to the base R, and you do here the divide by the commutators, have as differential little b you may take the cyclic bicomplex here, or this is the same module, but you take as operators little b plus capital B. You have to be careful because this complex is, as before, naturally contractible. And then you have the periodic cyclic complex, which is the completion of this. Okay, is that you take the completion of all this with respect to b plus b.
When you say it is contractible, you mean the
Homotopic
upper
to zero.
half plane? No, but the whole thing, not the right hand side as one usually takes.
It is a whole thing. You see here, you shouldn't really think in this way. Yeah, so it's really, yeah, but it says, okay, in some sense, it is the half plane if you want. So it's half plane, but things are not allowed to go up to infinity. Yeah, so it's in some bounded horizontal strip. Okay, your gadgets. Yeah, and so you can just contract them because the lines are contractible.
Yeah. But I mean, normally when you take cyclic cyclic homology is not zero.
Is what?
Cyclic
No, of
homology,
course. Yes, okay, I should say. I mean, I should say the following thing. This is somehow the skeleton of the cyclic complex. It's a contractible complex, but the algebra structure on A determines a natural filtration. And if you complete with the corresponding topology, you get a complex which is far from contractible and which gives you the periodic cyclic homology. So somehow the algebra structure is encoded in the topology, with respect to which you complete. It is not there in the beginning because this is contractible, but this is an interesting complex giving you a relative version of cyclic homology. Okay, now I come to the results I want to discuss. Maybe just one example. Just what is, if A is unital, what is HP of AA? For A unital. So this is the commutator quotient of A in the even case, and it's 0 in the odd case. Little exercise, okay? And if you ask, what is this good for? I mean, they are certainly extremely difficult to calculate, but this is not what we are interested in. What we are interested in is that some of the well-known results on cyclic homology carry over. For example, you can ask, under which conditions does Cuntz-Quillen's theorem hold that periodic cyclic homology does not see nilpotent extensions? Is there homotopy invariance of the homology of these complexes? Does excision hold? And for example, for Cuntz-Quillen's theorem, there is a quite a simple criterion, namely, if you have a nilpotent extension, is a nilpotent extension, and if you suppose that it splits in the category of R bimodule, so it's an R bimodule splitting extension with R bimodule splitting thing, then Cuntz-Quillen tells you that HPA relative to R to HPB relative to R will be an isomorphism. Okay, so this is quite straightforward. You just copy the proof word by word, and this is what you can do with that theory. Fine. Now I want to discuss the periodic cyclic homology of cross products. Finally, So calculation of HP, calculation. Of HP of a cross product G. So what we do here, we will look at a huge chain complex, and then we will calculate it in two ways just by taking two different bases of it. Okay, and this is all we do, and then the results just drop automatically. So what we do is the following. We start with a given G algebra. We tensorize it as an algebra with a stupid algebra. So AG here, I should say, AG, it's forgotten, this is just A tensor over K with KG. Okay, and the G action is the diagonal action now we use. So the G action on this algebra is free. And as there is a G action, I can take the cross product with G. I am interested in the periodic.
Sorry, the G action on the K of G side is translation.
Left translation. Left translation, excuse me. Thank you very much. So I use here, I let G act on A by the given action, and it acts here by left translation of this copy of G. And I look at the periodic cyclic complex to this, but relative to the group ring. So this is the complex I'm looking at. And a typical element will be written, can be written as, let's say it here, UG0, A0, H0, tensor UG1, A1, H1, tensor blah, 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 UGN, AN, HN. Okay, etc., etc., etc. Now, it's not so easy to work with this because there are many relations. And what you would like to do is to find a basis so that you can write elements in this complex in a canonical way. And now the main point is, the surprising point is that there are two ways. Are two ways to write elements canonically. Ways to write elements canonically. And this is expressed by the following two lemmas. Namely, the first lemma is, I will explain why there are two ways. Look at this algebra, it's pretty big. It contains on the one hand, clearly, a copy of this algebra here, this stupid algebra, but it also contains a copy of the cross product of only A itself with G. And this will be the observation of the first lemma. Namely, the first thing is the map J from the cross product of A and G to the cross product of the stupid algebra of G, which sends an element. I will write it like this, UGA. I have to write the group element here on the left-hand side, to UG A times here just the basis vector corresponding to the trivial element is an algebra homomorphism. So this is first observation. And the second observation is the induced map of complexes, of cyclic complexes to the cyclic complex of this algebra relative to the group ring. This is an isomorphism. It remains an isomorphism on a completion. Yeah, and I don't write it down because writing down is increasingly difficult. But the reason is that just this algebra here is a free bimodule over the group ring with basis J of A. Yeah, so this is responsible for this isomorphism. It's a very, very simple calculation. Yeah, and this is the first lemma. The second lemma is now the following. That when you look at the here now we just go only for the homogeneous part. There's a version of the lemma covering everything, but I'm only here interested now in the homogeneous part for simplicity. Genus part, namely the inclusion here of the stupid algebra, the standard inclusion into its cross product with G induces a map from CC of A clock G to CC of this algebra here, our big complex, relative to KG. And now this is not an isomorphism, but it factors through the G co-invariance, and this is an isomorphism. And let me explain why it factors through the G co-invariance. So, and why it is surjective. For this, we need to have a look here. Excuse me, this is it has to be the homogeneous part here. Okay. So suppose that we have an element here in the homogeneous part. So this means here we have tensors UG0, UG1 to UGN, whose product equals the unit element. And we have to show, excuse me, that they can be represented by a tensor here, which just has no non-trivial group elements. There are no non-trivial elements in the group ring. So what to do? Now the idea is you shift these factors UGN to UG1 just to the first digit. How can you do it? I mean, the tensor product is taken over the group ring. UG1 is in the group ring. You may shift it around here. You have a commutation relation allowing to shift here, and your UG1 ended up here. The same you can do with UG2 until UGN, but here we are in a cyclic situation. So to say, in a circle, you cannot go not only go this way with you to bring your GN to the first digit, you can turn around the circle as often as you want. And whenever you turn the UGN around all the tensors here, you just multiply the whole expression by the group element GN. And so this is why this factors through the co-invariance, and you have this. And now I'm able just to give the proof in 2 lines, or I can calculate in 2 lines at least the homogeneous part of the cross product. So this is just isomorphic to, let's see, the cyclic complex of the cross product is isomorphic to this complex. So this is isomorphic to the homology of the huge complex I consider A, G, cross product with G relative to the group ring, and I take here just the homogeneous part, the contribution of the unit element. This is true by the first lemma, but the second lemma tells me that this homogeneous part is just equal to the co-invariance of the cyclic complex And here, same thing for completions of the stupid algebra. Yeah. The co-invariance of this. But now, what is this? I mean, usually it is difficult to understand what happens after passing to co-invariance under group action. But remember, this is a G, the stupid algebra is free as a G module. So this is a complex of free G modules. Modules. Okay, so this means then, if you know homological algebra, that this is the so-called hyperhomology of G with coefficients in this complex. And hyperhomology has a nice property, namely quasi-isomorphisms of complexes induce isomorphism in hyperhomology. So now I know from Goodwilly's theorem that here this is a nilpotent extension of A due to the nilpotence of the stupid algebra. And because of Goodwilly's theorem, this is an isomorphism. And this is Nistor's result. And I will just, I know I'm already over time, but I will show you just a closed formula which gives the elliptic part. That means the contribution of all. So I mean, this is the first thing I should say. This kind of argument works for all conjugacy classes. And you get a particularly nice formula when you look at the conjugacy classes of torsion elements. This gives you the so-called elliptic part. Namely, the elliptic part is the contribution of all conjugacy classes of torsion elements different from the unit element. And you get that HP star A cross product with G elliptic is the following. It is the hyperhomology of the full group G with coefficients in a direct sum of complexes. This direct sum is over all torsion elements except the unit elements. So 1 is smaller than the order of V, is smaller than infinity. And here we take now the ordinary cyclic bicomplex of the cross product of A with respect, excuse me, so this time is so advanced, I forget notations. For an element in the group here, I call ZV the centralizer of V in G. It contains the cyclic subgroup generated by V as a central subgroup, and the quotient here is called NV, as you know. Okay, so what do I do here? I take the A, I take the cross product with a cyclic subgroup generated by the element V relative to the group ring of the finite cyclic group U. This has a homogeneous decomposition over the conjugacy classes of U, but U is an abelian group, so a conjugacy class consists of single elements, and I take the conjugacy class of the single element V. So this is a huge complex. I complete it with respect to the Hodge filtration on all of these, and that's it. Now, so I reduce the calculation of the periodic cyclic homology of this cross product, at least for the elliptic part, to the homology of G with coefficients in the cyclic complexes calculating the cross product with respect to these finite cyclic groups, or part of the cross product of these finite cyclic groups. Yeah, and this gives a nice closed formula. And I'm sorry, I will still one element to tell you that this new approach finally allows to tackle the problem of topological algebras, namely when you have gamma, a group acting discrete group acting properly isometrically and co-compactly on a cut zero space, on a space of non-positive curvature. So this was a category of groups where nothing was known up to now about their local cyclic homology. Then the local cyclic homology HC star log of the group Banach algebra L1 gamma, which is the same at the same time the analytic cyclic homology, if you prefer this, of L1 gamma, is isomorphic, and here, so to say, between all the conjugacy classes is isomorphic to the hyperhomology of gamma with coefficients in just the vector space spanned by the torsion elements in gamma, which becomes a G module under the adjoint action. So you get a complete description of the local cyclic homology of these group Banach algebras from this approach. Okay, I stop here because the time is over since a good moment.
Wonderful, wonderful.
Yeah.
Yeah. Does anyone else? I have some questions, but does anyone else have questions before I? Okay, so can you go back?
Yes.
Let me see. I don't know if it was the previous one. Yeah. Wait. So, yeah, when the class, no, the other one. There was one. Yeah, this one, I think.
Okay.
So, do you get instead of
you mean what happens if I take everything and not only the homogeneous part?
No, if you take, if you take, what I imagine is if you take another conjugacy class, do you get tensoring with what?
Okay, I will just write down what you get globally. So we'll deal with all conjugacy classes simultaneously. Yeah.
Okay.
So you get, there's a linear map starting from the group ring KG tensor CC of A G to CC. Yeah, I want to make it more precise because this is viewed as a G module, but on the adjoint action. So I allow myself to write K at G. So it's a linear span of G itself, but the action is the adjoint action to CC of A cross product, no, A stupid algebra with G, cross product G, blah, blah, KG, and now everything. And I will just describe the map. So here you have a basis element, let's say UG, tensor, and here we just have A0, H0, tensor, tensor, AN, HN. Okay. So that's a standard element here. And we map it here just to UG, A0, H0, tensor 1 in the group ring, which doesn't count, A1, H1, tensor nya, AN, HN. Okay, and this guy now, if we take, first of all, passes through co-invariance, and there it is in isomorphism. And so you get the full complex here described. Yeah.
Yeah.
And so somehow the principle, maybe I can explain okay, there is a question in the chat. Let's have a look. in your last result, analytic homology of the group algebra with HP. No, okay, I will ask this in a second. Yeah, but I will want to come here to describe, I mean, this result and also the previous lemma, which was this one. I can describe it best when I say there is two ways to write it canonical. I mean, you have lots of relations because you can move around the group, the elements in the group algebra across the tensors. And so there is one normalization condition here where you can go for the condition that H0 equals H1 equals Hn equals the unit element. And this leads to the first lemma, which is here. Yeah. And there's another normalization condition where you go for, this is the first one. And the second one, you can use the relations you have to achieve that G1 equal G2 equal Gn is 0. Yeah, and this gives you the other isomorphism. Yeah, so it's really just playing around with this complex. Okay, and this gives you one of these normalization condition gives you isomorphism here. The other gives you the isomorphism there, which is because it preserves Hodge filtrations, of course, extends to completions here. Okay.
Okay.
That's automatic. Huh?
But wait a second, sorry, a stupid question, but you wrote KRG.
Yeah, it means that it's a group ring. So at G is the set G, but equipped with the adjoint action.
Okay. So this is a
so
G module.
this is just as a linear space. It is a group ring, but it is viewed as a G module, and the adjoint action. Okay. Here it is the action. Here on A you have the given action. On the stupid factor, it's left translation, and then this is a map. So this map is so to say that this map here factors through co-invariance. And the reason is simple, because all the G action here is given by conjugation with elements in a group ring. But as you may pass elements in a group ring across the tensors, I mean, all these cancels completely. Yeah, because when I take a first factor here, let's say G A0 G inverse tensor G A1 G inverse tensor nya 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 nya, and I'm allowed to pass G across the tensors, G and G inverse will cancel. So that's why the action of why it passes through co-invariance. Yeah. So the calculations are completely elementary.
And and then the $1 million question is, how do you make sure that the convergence conditions?
You mean in the analytic case? Okay,
Yeah.
I will just tell you in the analytic case. In the analytic case, there is a rule: never mix up Z-graded and Z2 graded gadgets. So in the analytic case, what I do is I look at a so-called tilting complex, namely, I look at a nice projective resolution of the constant gamma module G. So this will be something like a Rips complex, or actually a limit, a formal inductive limit of Rips complexes of gamma. They provide a nice projective resolutions of the groups in questions. And I tensor it here with a suitable completion of the cyclic bicomplex of the stupid algebra. But one has to be careful here, namely, the topology I have to put here does not come from any topology on this algebra. It's a new kind of topology of the whole cyclic bicomplex here. Yeah. So in some sense, usually, if you would take for your had the group ring here and would have some L1 algebra of rapid decay, you would say that group elements of large lengths have big norms. Yeah. and of small lengths have small norms. But here it's so to say, here tensors where the elements G0 to Gn cluster together have small norm, and the norms grow exponentially if the elements in this cluster are taken to push to far distance from each other. Yeah. So the norm here is actually translation invariant and only looks at the distance between the elements G1, G0, G2 in the tensor. So this is a huge complex on which gamma acts. And now this is a complex of free G modules, of free gamma modules. This resolution is contractible to a point. It is non-equivalently contractible, yeah, because it's a resolution. But if I tensor a non-equivalently contractible complex of gamma modules with a complex of free gamma modules, it becomes equivariantly contractible. And I have an equivariant contraction onto, I should write it here, onto CCK gamma, just because this resolution retracts onto the point. But I can do it also in the other variable. I know that this is a complex of free gamma modules, and this is contractible. I mean, first of all, we would say, okay, Goodwillis theorem tells you it is contractible because it's a nilpotent extension of the ground field, and the analytic cyclic complex of the ground field is just the constant. But no, this argument doesn't work. Because the clusters you have to stay together of points. And this is here where you use the fact that you have a cut zero space. Now the distance on a cut zero space is convex. So when you push points towards the origin, if they were close to each other in the beginning, they will close to each other during their journey. And it's easy to contract this complex. Why? I can just look at the map from gamma to gamma, where I send just every point in gamma towards the origin in gamma. So when I have an element of word length n, I just push it to an element of word length n-1, etc., etc., etc. So I just represent it by any word of minimal length, and then I go there, and all these are just maps of sets from gamma to gamma. So they are algebra homomorphisms here. And this is a periodic cyclic complex. And so I know that there's a Cartan homotopy formula. And that's all I need. Yeah. So I mean, just everything completely basic. And then with this, I retract it here. And I know, so here I have a non-equivalent retraction because I just, in the cut zero space, I push everything towards an origin. So this is non-equivalently contractible. But I tensor it with a free complex of free gamma modules, so it becomes equivariantly deformable onto C star rips of gamma. So the rips complex is a deformation retraction of the tilting complex. This complex is a deformation retraction of the tilting complex. These retraction deformations are, everything is equivariant. So I may pass to co-invariance under the gamma action. I still have a deformation retraction here and here. And what do I get here? This is just the Rips complex. It's a resolution of gamma. I take co-invariance. Get the homology of gamma. And actually I have to take here, be careful about the coefficients. I didn't, no, it's here only for the homogeneous part. Excuse me. I just take gamma C. And what do I get here? Just from a lemma, previous lemma, it is the analytic cyclic, is the homogeneous part of the analytic cyclic complex. Here, okay. And for the other conjugacy classes, I do a similar thing, or to be precise, I show that the conjugacy classes of non-torsion elements do not contribute, and I have only finitely many conjugacy classes of torsion elements, where instead of just contracting everything to a base point, I look at the torsion element, I look at its fixed points under reaction on the cut zero space, and I project onto this convex subset. But I mean, everything is, so to say, technically pretty much the same for each conjugacy class. And so I arrive at this, yeah. Okay.
Yeah. So, I mean, over the years, every time we have discussed cyclic homology for cross products and group algebras and so on. In this analytic or local, you always emphasize that you cannot split the conjugacy classes.
Yes.
But here it appears like you could in this particular
case. No, this is the case because just you can treat all conjugacy classes of non-torsion elements simultaneously. The contribution is just 0. You do not have to split, just you kill all of them except for finitely many. Yeah. And the single conjugacy class is split because you have L1. This would not be possible if you take another completion. But you see, I mean, Guillermo, you see it already in periodic cyclic homology. Because when you look at the periodic cyclic homology of a group ring, on KG, yeah, this is neither a direct sum nor a direct product of the contributions of the conjugacy classes, because you see this the ordinary cyclic bicomplex, which is contractible of KG. This is a direct product of contributions coming from the conjugacy classes. Okay, so this is because the differential forms, the algebra of differential forms over KG decomposes according to the conjugacy classes. But in order to calculate this, I have to complete here. So I have to complete here. And the completion gives you something which is not a direct sum. So this decomposes neither as a direct sum nor as a direct product. So you see it already in the periodic cyclic theory that you have to be careful. Yeah. So the contributions of a single conjugacy class, you can split them off here. But when you want to split the overall conjugacy classes, you have neither a direct sum nor a direct product. Okay.
And this hypothesis that you put at the beginning about the group having finite homological dimension.
Yeah, homological dimension. This is okay. I can explain you why. Because, so to say, a very accurate or bureaucratic person would have said, what the hell is this? You take the hyperhomology of G with coefficients in a Z2 graded complex. And it is only defined for Z graded complexes. And here I cheated a bit. I mean, so to say, first of all, I say, this is a complex of 3 G modules. So the homology of coinvariance is the hyperhomology. One has to say, stop, this is in general false for Z2 graded complexes. And it's the really technical part of my paper is to showing it is justified in this case. The same is here. The fact that this is a quasi-isomorphism does a priori not imply that you get an isomorphism in hyperhomology if your groups are Z2, if the complexes are Z2 graded. It is still true here. And now if you're let me tell you what happens if the group is of infinite homological dimensions. How do I define the hyperhomology? So this is a question which comes up here. What is hyperhomology with coefficients in a Z2 graded complex? Some CC hat, which is Z2 graded. So what you do, you start with a projective resolution of the constant G module. Okay. So this is projective G modules. Projective G modules. Then you turn this into a Z2 graded complex just by putting together even and odd part. Then you tensorize with CC. and I take the coinvariance. And I say, find this complex calculates hyperhomology. Now, when the group is of infinite cohomological dimension, this Guy resolution is of infinite length. And in order to calculate here the periodic cyclic homology, I have to complete everything. But it means here I get the periodic cyclic complex. Here I get a completion, and I have to complete the tensor product. And this is what I call in the paper just hat. Okay. And here I just supposed finite cohomological dimension because I did not want to take my time to explain you what the hat means. Yeah, that's the whole difference. If this is of finite length, you skip with it and you stay with the ordinary tensor product here. Okay.
Just a couple of remarks.
Yes.
Ill-meant remarks.
Sorry, ill-meant remarks.
Yeah. So you write the symbol of the cross product with G. You put the G on the right. But then when you wrote the elements, your UGs went to the left.
Yes. Okay, I can tell you why. Because I just from the beginning I wrote the stupid multiplication like this. Okay. And then I run into trouble with the lemmata if I write the cross product in the usual way. Of course, I could have just as well be so wise to take as stupid multiplication that one. So this is just the opposite algebra. Yeah. And then I would have just to use the cross product in the usual way to get the formulas I want.
Yeah, but what I'm just saying is that if you're going to put the UGs on the left, the symbol that you use to the
is on the right.
You could put the G on the left. I mean,
I could put the G on the left. You are right. Maybe this would have been more intelligent, but it's still the same algebra.
Yeah. It's just saying that you probably.
But I can tell you what the problem is, because I said that maybe this is just last formula. I said that this map, when you look at these maps, these elements, UG A times E, the multiplication U, let's say H, B, E. So I said that adding this symbol E is a homomorphism of algebras, and this is non-trivial. Look what happens when I multiply these. I make the UH pass here, so I have to act with H inverse. So this is UGH times H inverse of A times H inverse of E, which is H inverse, times, so the H is again here, times B times E. And what is this? This is UGH. Here they commute, those guys. This is H inverse of A times B times the product of H inverse and E. But it's the stupid product. So this is again E. And this is just the product UGA UHB times E. And this would be wrong if I write UG on the other side, yeah? Then I would, so to say, have to define this stupid product differently, because then I want to say, okay, E times H has to be E, yeah?
Yeah.
Okay.
Yeah, I see. Just one more comment. I have a paper which nobody read.
Okay.
Whose title
I have a couple of them.
No, yeah. Called the derived functor analogy in Cuntz-Quillen framework for cyclic homology.
Okay.
Yeah. So I suppose, I mean, I was reminded of that when you mentioned the Quillen's. This goes, I mean, Quillen's idea was to use it in the non-commutative world, but in the commutative world, it, I mean, appeared already in Harshon's famous paper on Grothendieck's the RAM homology, and I think in Grothendieck himself. But, okay, so if there are no other questions, I will stop the recording.
Okay, or maybe maybe a final remark to say why I take the stupid multiplication x to y is y and not to x. I mean, this is so to say the starting point of the whole story, maybe, because you might look at the Hochschild complex of the stupid algebra. Yeah, and as I said, it is H unital in a very strong way. So it means that this can be calculated, is chain homotopy equivalent in a natural way just to the complex omega star of kg. No, stop, nonsense. Tensor powers, excuse me, this is kg. Tensor, okay, n plus 1 in degree n. And the differential is just small b. And then it's a straightforward exercise to calculate this complex. And what do you get? You get, or g of x, excuse me. It's true for every set. And what do you get? You just get the bar construction over x. So that's the key idea behind everything. That the bar construction over a set may be interpreted as the Hochschild complex of an algebra. And then when the cyclic homology of this algebra or the periodic cyclic complex of these algebras are the right things to deal when you want to pass from the Hochschild homology of a group ring or a cross product to the cyclic homology of a group ring of a cross product or a cross product. And that's wrong if you take the other. If you take x, y equals x, you get, so to say, the bar complex twisted by a cyclic permutation. Okay. So this gives you also the link to the work of Burgeli and Nistor. Yeah. So they work with chain complexes, resolutions, and I always stick just to algebras. I always stick with non-commutative, highly non-commutative universal algebras. And all I use is just Goodwillis theorem, or in the analytic case, the homotopy invariance of analytic cyclic homology. Yeah. And this is in some sense the same calculation, but I stick more to the point. Yeah. So I mean, also to say all the terms, all the gadgets I use are much more flexible, because the bar construction is a rather rigid thing when you look at it at the first sight. But here it becomes, from this point of view, it becomes completely flexible, because once you pass from a Hochschild to a periodic cyclic complex of your stupid algebra, you notice there are so many automorphisms and homomorphisms of the stupid algebra to itself, or between stupid algebras. You have a whole wealth of formulas or possibilities to manipulate these complexes. Whereas when you look at the bar resolution, it appears rather rigid. Yeah, so that's the philosophical background behind it.
Okay. So we'll stop the recording now.